Okay, so yesterday we left off with this diagram. We were showing basically all the space missions that went to different places in the solar system. I think I was telling you about the Venera probes, the Russian probes that went to Venus, right? How all those people probably ended up in salt mine Siberia or failure. Yeah. Okay. So there were a lot of missions, and you can see here that all the faded lines, all the darker lines, are failures, and there's a lot of them. Because getting probes to other planets, especially probes that have to land on the surface, is, well, hit or miss. Okay? I mean, for a while we were batting under 500 for landing things successfully on Mars. Okay? And the challenge being that on Mars it's hard to slow things down. On Venus, Venus wants to crush them by slowing them down really fast. Okay? And then using its super dense atmosphere to destroy things. Okay. On Mars, the other issue is, well, it's hard to slow down, so you might crash, but also you're exposed to an incredibly cold, dry, barren environment where dust settles on your solar panels and makes you die if you're a probe. Okay. Which is why the latest probes that we have put on Mars are powered by RTGs, that is radio decay thermal generators. Okay, the same thing that Mark Watney used to heat the rover. Okay, he had that big thing of plutonium that he dug up that he wasn't supposed to dig up. Yeah. Okay. One of the lessons was don't dig up the big lump of plutonium, Mark. Yeah. So he did that anyway. That's actually what we're using. There was a lot of debate as to whether we should do that or not. Why? Why would there be debate as to using a nuclear power source on a spacecraft?
It contaminates the planet.
Yeah, either one. If it blew up during launch, it would spread radioactive material over a wide area because it has a radioactive cell in it. Okay? And similarly, it's going to die on Mars at some point, and we're going to leave a big chunk of plutonium sitting there forever. Possibly. We might go retrieve it at some point. Okay? The latest one does have that soil sample return ability that it's taking right now. Okay? But it's tough. It's tough to get things to land on Mars successfully. For a very long time, we were using the airbag landing method. Okay? So this thing would go through the atmosphere, it would use parachutes to slow down, and then as it neared the surface, it would inflate all of these airbags all around it and detach the parachutes, and it would literally bounce along the surface of Mars for several kilometers until it rolled to a stop. Okay? And then they would deflate the balloons in a certain order to get it to turn upright. Okay? And that was what we used to land things. The problem with that method is not that it doesn't work, it actually works very well. The problem with it is you can only land small things. Okay? So the rovers had to be quite small in order for that to work. We wanted to land bigger, more complex rovers, so we went to the sky crane method. Okay?
Yeah, don't they have like magnets that just like there's like a hover, almost like a carrier that comes and slows down a lot, and then eventually it gets to a certain point where it attaches the rover, and the rover has parachutes and has like thrusters on it to help slow it down even more.
Sort of, yes. So it has parachutes that slow it down to a certain speed. Okay, and then it uses basically a ring of retro rockets that will lower it and actually hover, and then there's actually a crane. There's literally a crane, okay, that lowers the rover by cable from this hovering ring of rockets. Okay, and so as it's coming down, and then just before it's on the ground, they actually blast the cable so that the retro rocket unit flies off and crashes somewhere. Okay? Because you don't want the rover to land and then have the ring of rockets come down on top of it. Okay? So they actually drop it about 8 feet, 10 feet, maybe more, okay? And actually just like unceremoniously let it clunk onto the ground. Okay? Now, it sounds like that's pretty reckless, like dropping something 10 feet that's worth billions of dollars and you had to fly all the way to Mars. But remember, on Mars, gravity is 1/3 of what it is on Earth. So if you drop something 9 feet, it's like only dropping it 3 feet on Earth. So it'd be like, okay, we got this heavy duty unit, we're going to drop it this far. It'll probably be okay. Okay. So it's quite a process to get it there. And the challenge is It all has to be done by
Yeah.
computer. Yeah. You cannot pilot it from Earth. Because it takes, if you're in a good situation, 10 minutes for a signal to go from Earth to Mars. And that's if they're close. Okay? If they're spread out further, opposite sides of the sun, you can't communicate at all. All right? So they generally try and land them when they're close so that that delay is lessened. But you can't pilot it because you'd make one correction and 20 minutes later, you'd know the result of it. Okay? That's not good for landing a spacecraft. And so it has to be all done by computer, which has been challenging because computers face a lot of problems during spaceflight. There's, radiation and particles and things like that that can damage them. Okay, but the purpose of showing you this was to show you how often we use the gravity slingshot to accelerate our probes to the distant parts of the solar system. Okay, so the two probes here, Cassini and Galileo, okay, they both went actually in and went around Venus, got a gravity slingshot from Venus, came back to Earth, got a gravity slingshot from Earth, okay, and then went out to Jupiter. Okay, Galileo stopped at Jupiter, but Cassini continued on to Saturn after getting a gravity slingshot from Jupiter, okay, and actually stayed around Saturn until we crashed it into Saturn a few years ago because it was at the end of its serviceable life. Okay, but it did a bunch of studies around Saturn and dropped a probe onto the surface of Saturn's largest moon in about 2007 or so. Okay, so quite a bit of stuff there. Okay, and you can see all of these lines all go around all of the planets. We're always using the gravity slingshot because we can't possibly carry enough propellant to accelerate these spacecraft and turn them and maneuver them, okay, without using gravity to help. Right? It would be impossible to carry that much fuel. All right, questions on that? Okay. Is the force of gravity a vector quantity?
Yes.
Yes, absolutely it is. All forces are vector quantities. So what we have to consider is that there could be multiple gravitational forces acting on a particular object. Okay? Okay. So there could be a kind of vector addition kind of thing going on with some gravitational interactions. So, look at an example here. Not that one. All right, before we do other examples, I'd like you guys to try these two because they're like what we were doing yesterday. Okay? They're simply using Newton's universal law of gravitation. So that would be that Fg equals big G times m1 times m2 over r squared. Okay? So using that formula, I'd like you to solve these two questions. Okay? Answers are right there so you know if you did them right or not. Okay? And we'll talk about those in a little bit here. Okay, so for number one, we're just plugging in the numbers, right? It just wants to know the force, the gravitational attractive force between these two people who are sitting on a bench together. Okay, so we're just going to plug in 6.67 times 10 to the minus 11, that's big G, okay, times their two masses, that would be 55 and 80. And over the distance they are apart, squared. Okay, so if we plug all that into our calculator, okay, we should have, so on the top, 6.67 e negative 11, and then 55 and 80, and then divide that by 0.6 squared. All right, so 8.2 times 10 to the minus 7 newtons. Is that very much? No. Okay, because of Earth's gravity, they're not going to be attracted to each other in any way, but even if they were out in space, it would be pretty hard for them to move towards each other, okay, with that weak of a force acting between them. Okay, so this is usually where this question comes up. If I got like bigger and bigger and bigger, would stuff start to move towards me? No. Okay. No, I mean like in a practical sense. Like if I continued to eat, would it get to the point where I wouldn't have to move to get food because food would come to me?
No.
No. Okay. You're never going to get big enough that would, you'd have to eat half the earth, okay, for that to happen, and that's not going to happen because probably a lot of it doesn't taste good. So yeah, you're never going to have an issue or a situation where something is going to move towards you on Earth because of gravitation. Everything moves toward the Earth because its gravitational field strength is so much greater than anything you could possibly make. Okay? All right, and that's kind of where the second question comes in that you're working on right now. The Titanic did not hit an iceberg because it was gravitationally attracted to it. Okay, it hit it because somebody was asleep at the switch and the captain was drunk. Something along those lines. Okay, so yeah, you should probably pay attention and not go real fast and think your ship is unsinkable, because as soon as you say that, your ship is sinkable. Yeah. Okay. All right, I'll give you a couple more minutes on number 2. Okay, let's have a look at the second one here. So we know the mass of the Titanic was 4.6 times 10 to the 7 kilograms. Okay, so we're going to say mass of the Titanic, 4.6 times 10 to the 7 kilograms. Okay, gravitational force exerted by the Titanic on the fatal iceberg was 61 newtons. Is that very much? No, that's next to nothing. It's 1/10 of what you weigh. Okay, so 1/10 as much as you are attracted to the Earth is how much the iceberg was attracted to the Titanic by. Okay, so we know the force of gravity, okay, 61 newtons, and we know that they were 100 meters apart. So that would be, our R, 100 meters. Okay, what was the mass of the iceberg? Okay, so we then need to manipulate this formula. Big G times the mass of the Titanic times the mass of the iceberg over R squared. I'm looking for the mass of the iceberg, so I'm going to multiply both sides by R squared, divide both sides by big G times the mass of the Titanic. That's going to leave me with the mass of the iceberg, so that will be 100 squared times 61 divided by 6.67 times 10 to the minus 11 times 4.6 times 10 to the 7. That will give me the mass of the iceberg. Okay, and then we're going to divide that by, in brackets, 6.67 e negative 11, 4.6 e7. Oh, missed the decimal. Okay, that looks like 2 times 10 to the 8 to me. Okay, so pretty big? Yeah, bigger than the Titanic. Okay. All right, questions on how that works? Okay, fairly easy formula to use, right? Okay, so this question here, not so much a math question as it is a understand how things affect the force of gravity kind of a question. So object A exerts a gravitational force of 1.3 times 10 to the minus 2 newtons on object B. Determine the magnitude of the gravitational force if the separation distance is doubled, mass A increases by 6 times, and mass B is halved. Okay, explain your reasoning. All right, so a lot of people will look at this question and go, they give me one number. How am I supposed to do this? Okay, and the answer is by factors, really. Okay, you don't have to factor it, but by factors. So let's just say in the first situation, okay, that the force of gravity is that number, but that is big G times 1 divided by 1 squared. Just for argument's sake, because they don't give us any of those numbers. Okay? In the second situation, they tell me that that mass A is going to increase by 6 times. So I'm going to have G now times 6, and the other one is halved. So times 0.5. And then the distance is going to be doubled. Everybody with me there? Okay, so what's 6 times 0.5? 3. Okay, so in this situation, I had 1 over 1 when I was done. Yes? Okay, in this situation, I'm going to have 3 over 4. So, in the second situation, the gravitational force is going to be 3/4 of its value in the first situation. What has a bigger effect, mass or radius? I put 3 times more mass in the second situation, but I only doubled the radius, and I'm less. Okay? So, does radius have a bigger effect than mass? Because it's exponential. Right, it's squared. That's all that question is trying to show you. Okay? Just trying to show you that, remember, separation distance, or R, has a bigger effect on the force of gravity than changing the mass does. All right. That's basically the same thing. All right, so this is a type of question that gets used a lot. Like, I've used it on unit exams many, many times. Right? It's asking you to calculate the net gravitational force on Earth. Okay? So these are the numbers we have. I'm going to alter them so they actually match what we have on our formula sheet. Okay? So on our formula sheet, this is 3.85 times 10 to the 8 meters. Okay? And this is 5.98 times 10 to the 24, and this is 7.36 times 10 to the 22. I don't know why their numbers are different, but they are. We're going to fix them. How do we usually calculate net force? 2 ways.
Sum of all forces and mass times gravity.
Right.
Acceleration.
Or mass times acceleration, which we're not going to use here, and the vector sum of all forces. So, in this situation, the Earth is being pulled in 2 different directions, agreed? There's a force of gravity between it and the moon, and there's a force of gravity between it and the sun. All right? Calculate the net force acting on the Earth when the Earth, moon, and sun are in this orientation. Give you a few minutes on that. You're calculating the net gravitational force acting on the Earth when they're in this alignment. Okay? And you're going to be needing this formula more than once. Okay? And you're calculating the net force. Give you a few minutes to think about that one. All right, so for this one, we've got 2 forces. We've got the force of gravity between the sun and the Earth, pulling the Earth towards the sun. And we've got the force of gravity between the moon and the Earth, pulling the Earth towards the moon. All right? So they're acting in opposite directions. One's going to be positive, one's going to be negative, and obviously the force of gravity between the moon and the Earth is smaller, otherwise, well, bad stuff would happen. Okay? So the Earth is obviously more attracted to the sun. So what I've got to do is do 2 separate calculations using Newton's universal law of gravitation. So force of gravity between the sun and the Earth is going to look like this. 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24, that's the mass of the Earth, times 1.99 times 10 to the 30, that's the mass of the sun, divided by 1.50 times 10 to the 11 squared, that's the distance between the center of the sun and the center of the Earth. Okay, so when I do that calculation, so 6.67 e negative 11, 5.98 e 24, 4, 1.99 e 30. 0 E11 squared. All right, So we're looking at 3.527 times 10 to the 22 newtons. So 3.53. Okay, and that would be toward the sun as a vector. Okay, I have to do a similar calculation between the Earth and the Moon. Okay, so the force of gravity between the Moon and the Earth, 6.67 times 10 to the minus 11 times 5.98 times 10 to the 24 times 7.36 times 10 to the 22 divided by 3.85 times 10 to the 8 squared. I'm trying to shortcut. This probably doesn't end up saving me a lot of time, but 7.36 22 3.85, not 3.82. No, I obviously messed something up there. Oh, because it squared it twice. That definitely didn't end up saving me any time. There we go, that's a better number. Okay, 1.98 times 10 to the 20 newtons. And that would be toward the Moon. Okay, because that's the direction the Earth would be pulled by the Moon. Okay, and it is in fact that force that causes the tides. Okay, so it's a lot of force. You can see why it would pull all of the water on Earth towards it. All right, so we've got those two forces, and they're acting in opposite directions. So what do I need to do with those two numbers? To find the net gravitational force acting on the Earth.
Subtract the Moon from the sun.
Yeah, just subtract the two. Okay, that's all there is to it. Okay, so if I'm looking for F net, okay, it's just going to be the force of gravity between the sun and the Earth minus the force of gravity between the Moon and the Earth. Okay, and so that will be that number minus that number. Okay, which gives me 3.51 times 10 to the 22. So like it barely has any effect. Okay, it's so much smaller than the force of gravity between the sun and the Earth, okay, that it only changes one decimal here. Okay, so we got 3.51 times 10 to the 22 newtons. What do you suppose if I put this on a test, people would forget to put on this number?
Right or towards the sun?
Towards the sun, because right would be wrong. Weird. Okay, yeah, right would be the incorrect direction. Towards the sun would be the correct direction, and that is what most people would forget. And then I would write it in big, angry red capital letters on their test, okay, for forgetting it. True story. All right, that one making sense? Like, that's not terribly difficult, right? Like, you didn't have to manipulate anything, you just had to do two calculations. All right. I mentioned I put that on a test before, right? Okay. All right, now try these two situations. So one of them, now we've changed the position of the Moon. That's all we're doing, is changing the position of the Moon. So now, in question number 1, the Moon is between the Earth and the Sun, so this is a solar eclipse, because the moon is going to eclipse the sun. In the previous example, it was a lunar eclipse where where the Earth would eclipse the moon. Okay, so I want you to calculate, and you don't really have to do a lot of new math here. This is like one step. Okay, calculate the net force of gravity acting on the Earth in this situation, and then do it for this situation. It actually still doesn't require you to recalculate the forces. The forces are going to be the same no matter what. Okay, but it's the vector part of it that's going to change. So I'll give you a couple minutes. It'll only take you like 10 seconds to do number 1, but number 2 will take you a little while longer. Okay, what did we need to do different for question number 1? Yeah, instead of subtracting them, we just need to add them. Now the moon is pulling towards the sun, so we simply add the two forces together. Okay, so if we go back to what we just did here and go get our entry back and just scroll back here to change the plus or minus to a plus. Okay, 3.55 times 10 to the 22 newtons towards the sun and moon. You could write either one in that case, and they would both be correct because that is the direction they're both in. Okay. How does number 2 change? Yeah. Now you got to do like tail to head kind of stuff, because now the two vectors are not collinear. Now they're perpendicular now. Okay, but they still create a situation where you've got to put those two numbers you already have. Okay, the 3.53 and the 1.98, okay, you got to put them into a Pythagorean theorem situation, okay, to get your overall net force. Okay? And just so you know, you're not doing anything wrong if you get a decimal for the angle, because the sun's gravity is that much stronger than the moon's, and so when the moon's off to the side, it makes very little difference. Okay, so is this drawn to scale at all? No, it's terrible. Okay, if this was, but the reason it's not drawn to scale is because if we drew it to scale, our vector diagram would look like this. This would be the force of gravity between the sun and the Earth. And that would be the force of gravity between the moon and the Earth. It's so minuscule compared to the gigantic force of gravity between the sun and the Earth that we would barely see it, which is why it creates a triangle that has an angle of 0.3 degrees in it. Basically, the hypotenuse and the adjacent side are the same length, okay, out by just a hair. Right? So that's why we see that number look that way. It's because it literally makes a triangle where the hypotenuse and the adjacent side are almost parallel. Okay? Because there's so small of a degree in between them. Okay? So all we really had to do was go that F net, right, would be the square root of the 3.53 times 10 to the 20 squared. Okay, plus 1.98, sorry, that's 22. 1.98 times 10 to the 20, that one's 20, squared. Okay, that gets us basically the same number, 3.52. Okay, sorry, this was 3.52 times 10 to the 22. Okay, and then we get that smaller, we get that tiny angle when we do the trigonometry, right? So we go 10 to the minus 1 of the opposite side, which would be 1.98 times 10 to the 20 over 3.52 or whatever it was times 10 to the 22, right? So we get that tiny little angle of 0.3 degrees. Okay? I have never asked one on a test where I actually made you do the perpendicular one, okay? But it's not a bad review, okay, of the vector addition stuff we did in previous units. Okay? I usually make it so it's either a lunar eclipse or a solar eclipse if I do it. All right, questions on either of those? Okay. So in your digital workbook, I'd like you to work on a couple of these, and then tomorrow we're going to start on satellite motion. So in your digital workbook,
It is gonna be on page 3, bottom of page 3 and top of page 4.
Okay, so those are the ones I'd like you working on. Okay, universal gravitation worksheet there, bottom of page 3, top of page 4. Okay, none of those are terribly complex, but it's just good practice. And then tomorrow we'll start talking about satellites, okay, and how they work. And then gravitational field strength on Friday, super short lesson. I'll do the unit exam review on Monday. Actually, no, I'll do the unit exam review Friday. I'll do gravitational field strength on Monday. Okay, that way you can study over